Welcome! In this session, we'll be diving into problem number 1140, Stone Game 2. This is an exciting problem that involves dynamic programming and strategic decision-making between two players, Alice and Bob. We'll explore different approaches to solve it and analyze their time and space complexities. Let's get started. In this problem, Alice and Bob are playing yet another game with piles of stones. The piles are arranged in a row, and each pile contains a certain number of stones, represented by the array called piles. The objective is straightforward: maximize the total number of stones collected. Alice always takes the first turn, and the game continues until all the stones are taken. Both players play optimally, meaning they make the best possible moves to maximize their own total. The twist in this game is the parameter m, which starts at 1. On each turn, a player can take up to 2 times m consecutive piles of stones. After their turn, the value of m is updated to the maximum of its current value and the number of piles the player just took. The challenge is to determine the maximum number of stones Alice can collect if she plays optimally. Consider the first example where the input is piles equals 2, 7, 9, 4, 4. Alice begins with m set to 1, which means she can take up to 2 piles. She decides to take the first pile, which contains 2 stones. Bob then takes his turn, also starting with m equal to 1. He chooses the next pile, which contains 7 stones. Now, it's Alice's turn again, and m remains at 1 since neither player has taken more than 1 pile. Alice opts to take the next 2 piles, which contain 9 and 4 stones. By the end of the game, Alice has collected a total of 2, 9, and 4 stones, giving her 10 stones in total. This is the maximum she could collect by playing optimally. Now, take a look at the second example where piles equals 1, 2, 3, 4, 5, 100. Alice starts with m equal to 1 and decides to take the last pile, which contains 100 stones. This is a strategic move because it allows her to maximize her total early on. Bob takes the next turn with m still at 1 and chooses the first pile, which contains only 1 stone. Alice's m remains at 1 for her next turn, and she decides to take the next 2 piles, which contain 2 and 3 stones. By the end of the game, Alice has collected 100, 2, and 3 stones, giving her a total of 104 stones. This example illustrates how optimal play involves not just maximizing the current turn but also planning ahead. The constraints of this problem include arrays of length up to 100, with each pile containing between 1 and 10,000 stones. Edge cases include scenarios like a single pile, where Alice simply takes it, or piles with equal values, which test strategic alternation. Efficiency becomes crucial when dealing with larger inputs or high values, making this a challenging yet rewarding problem to solve. To solve Stone Game 2, we first considered a brute force approach. The intuition here is straightforward, since the game involves 2 players, Alice and Bob, taking turns in choosing between 1 and 2 multiplied by the current value of m piles. We could simulate every possible move recursively. In this approach, we would explore all combinations of moves for both players, evaluating every game state, including the remaining piles, the current m value, and whose turn it is. This creates a tree-like structure where each node represents a game state. However, a key observation is that the number of states grows exponentially as the number of piles increases, leading to an exponential time complexity, roughly 2 to the power of n. This makes the brute force solution impractical for larger inputs. Instead, we turn to an optimized dynamic programming approach. Here, the game's overlapping subproblems and optimal substructure make it an ideal candidate for memoization. By storing the results of previously computed states, we can avoid redundant calculations and significantly improve efficiency. The key idea is to define dp m as the maximum stones the current player can collect starting from pile I with the given m value. Transitioning between states involves considering all valid moves, where the player maximizes their score while accounting for the opponent's optimal response. In this dynamic programming formulation, the transition relation is central to understanding how the problem is solved. Specifically, dp m is calculated as the maximum value of the total number of stones remaining, sum piles I minus the opponent's optimal score, represented by dp I plus x max m x. Here, x ranges between 1 and 2 multiplied by m, representing the number of piles the current player can choose to take, as long as the choice remains within bounds. This dynamic calculation ensures that each player acts optimally, aiming to maximize their own score while minimizing the opponent's potential score. Now, if we analyze the time complexity, there are O(n) possible starting piles and O(n) possible values for m, resulting in O(n²) states. For each state, we evaluate a range of up to 2*m moves, leading to an overall time complexity of O(n³). The space complexity for memoization is O(n²), as we need to store the results for each state. However, we can optimize space further. By noting that dp(i)m depends only on future states, we can reduce the space complexity to O(n) by maintaining only the current and next states during computation. This makes the dynamic programming approach not only efficient but also adaptable in terms of memory usage. Considering the options, the optimized dynamic programming approach was chosen as the best strategy due to its balance between complexity and performance. While the brute force approach is simpler conceptually, its exponential growth makes it infeasible for larger inputs. On the other hand, the DP approach, though slightly more complex to implement, scales well within the problem's constraints, such as a maximum pile length of 100. Additionally, it effectively addresses overlapping subproblems through memoization, ensuring that redundant calculations are avoided. This allows the solution to achieve a time complexity of O(n³), which is manageable within the given constraints. Overall, the optimized DP approach strikes the right balance between correctness and efficiency, leveraging the problem's structure to deliver a solution that is both practical and robust for competitive programming scenarios. This problem revolves around a game with two players, Alice and Bob, who take turns picking stones from an array of piles. The ultimate objective is to maximize the number of stones that each player collects, with both players playing optimally. The number of piles a player can pick in one turn is determined by the value of m, which starts at 1 and dynamically adjusts based on the maximum of the current choice and the previous value of m. Our task is to compute the maximum number of stones Alice can collect if both she and Bob follow optimal strategies. To solve this problem efficiently, we use dynamic programming. The key is to define dp(i)m as the maximum number of stones a player can collect starting from index I with the current m set to m. Ultimately, the solution boils down to computing dp(0)1, which captures the maximum stones Alice can collect starting from the first pile with an initial m value of 1. Now, let's look at the recursive relation that drives our dynamic programming solution. When a player picks x piles, where 1 equals x equals 2*m, the remaining piles start from index I plus x, and m updates to the maximum of its previous value in x. The recurrence relation is expressed as dp(i)m equals max sum piles I plus x plus sum piles I plus x dp I plus x max m x. Here, the first term represents the stones collected by the player, while the second term accounts for the opponent's optimal score, which is subtracted because both players aim to minimize the other's total. The base case is simple: if the index I exceeds the length of the piles, there are no stones left to collect, so dp(i)m equals 0. To optimize calculations, we pre-compute suffix sums in an array called suffix, where suffix I gives the cumulative total of stones starting from index I. This allows us to compute subarray sums efficiently as suffix I, suffix j, reducing redundant calculations and improving performance. Finally, the solution is implemented iteratively using a bottom-up approach, starting from the end of the array and moving backward. In the bottom-up dynamic programming approach, we calculate dp(i)m iteratively for all valid indices I, multiplier values m, and choices of x, using the recurrence relation we just derived. The iterative process ensures that we build solutions for smaller subproblems first, which are then used to solve larger ones. At the end of the computation, the final answer is stored in dp(0)1, representing the maximum stones Alice can collect when starting with the first pile and an initial m of 1. There are several key insights to highlight here. First, the dynamic update of m provides increasing flexibility in the player's choices as the game progresses, which is critical to modeling the problem accurately. Second, subtracting the opponent's score ensures that the algorithm accounts for both players playing optimally, creating a robust strategy. Lastly, pre-computing the suffix sum significantly reduces the complexity of summing subarrays, making the solution scalable for larger inputs. Together, these insights form the backbone of an efficient and optimal solution to the problem. The algorithm's efficiency can be analyzed in terms of both time and space complexity. The time complexity is O(n squared), as we evaluate each state I for up to n possible values of m and iterate over valid choices of x. The space complexity is also O(n squared), due to the 2D dp table, while the suffix array adds an additional O(n) space overhead. With the optimized structure in place, here's the pseudocode for the implementation. First, pre-compute the suffix sums to enable quick range queries for summing subarrays. Then, initialize a 2D dp table to store the results for each state. Using a bottom-up approach, iterate over the indices I in reverse and evaluate all valid values of m and x, updating the dp table using the recurrence relation. Finally, the result is stored in dp 0, 1, which represents the optimal score Alice can achieve. This pseudocode effectively captures the essence of the algorithm, ensuring clarity and efficiency in solving the problem. Here, we start by defining the StoneGameII function inside the solution class. The first step is to calculate the number of piles, denoted as n. To efficiently compute the total number of stones remaining from any given position, we create a suffix_sum array. This array helps us keep track of the cumulative sum of stones starting from the last pile and moving backward. The last element of suffix_sum is simply the last pile, and for each previous pile, we add its value to the sum of all the piles to its right. This pre-computed array allows us to quickly access the total stones from any given index without recalculating it repeatedly. Next, we initialize a memoization table, dp, which will be used to store intermediate results and avoid redundant computations. The core of our approach lies in the DFS function, which takes two parameters, index, representing the current pile, and m, the current value of the multiplier. The base case checks if we have reached the end of the piles. In this case, Alice can no longer take any stones, so we return 0. Another important scenario is when Alice can take all remaining stones. This happens when 2*m is greater than or equal to the number of piles left. In such cases, we directly return the pre-computed value from suffix_sum. Finally, before diving into recursive calculations, we check if the result for the current state, defined by index and m, is already stored in dp. If it is, we return the cached result to save computation time. The heart of the solution lies in determining the maximum number of stones Alice can collect for each state. To do this, we initialize a variable max_stones to 0. Then, we iterate over all possible moves Alice can make, which range from taking one pile to 2*m piles. For each possible move, represented by x, we ensure that Alice doesn't exceed the bounds of the array by checking that index plus x is less than or equal to n. The key idea here is to minimize the stones the opponent can collect in their subsequent turn. This is achieved by recursively calling DFS for the next state and subtracting the opponent's best outcome from the total stones available at the current index. The max function helps us ensure Alice's score is maximized across all possible moves. After computing the best outcome, we store the result in our dp table for the current state defined by index and m. Finally, the result is returned. To initiate the game, we call the DFS function starting from the first pile with an initial multiplier m equals 1. This setup ensures that Alice begins the game optimally and that the result of the function gives us the maximum stones she can collect. Here, we begin implementing the solution for the StoneGame2 problem in Java. First, we import the necessary utilities and define our solution class. The main function, StoneGameII, takes an array of piles representing the number of stones in each pile. We calculate the length of the array and then construct a suffix_sum array. This suffix_sum helps us efficiently calculate the total number of stones remaining from any given index to the end of the array. Starting from the last pile, we initialize the suffix_sum to the value of the last pile and then iterate backward, adding each pile's stones to the cumulative sum stored in the next index. This gives us a quick way to access the total stones from any position. Next, we define a memoization table using a hash map to store previously computed results, which will help us avoid redundant calculations. Finally, we call a helper function DFS that performs a depth-first search with memoization, starting from index 0 and an initial value of 1 for m, the maximum number of piles Alice can choose in the first move. The DFS function is designed to calculate the maximum number of stones Alice can collect starting from a given index and with a specific value of m. If the index reaches the end of the piles, there are no stones left to take, so we return 0. Next, we check if Alice can take all the remaining stones in one move. This happens when twice the value of m is greater than or equal to the number of piles left, in which case we return the total from the suffix sum at the current index. If not, we compute a unique memoization key using the current index and m. If this key already exists in the memoization table, we directly return the stored result to save computation time. To find the maximum stones Alice can collect, we iterate through all possible choices for the number of piles she can take, from 1 to 2 *m. For each choice, we calculate the stones Alice can collect as the remaining stones minus what the opponent can force her to leave. The result of these iterations is stored in max stones and eventually saved to the memoization table before being returned. This ensures that we explore all possible strategies efficiently while avoiding redundant calculations. We start by considering the problem where the piles of stones are represented as 2, 7, 9, 4, 4. The first step is to calculate the suffix sum, which helps us quickly determine the total number of stones remaining from any index onward. Starting from the last pile, we calculate the suffix sums as follows. The last pile contributes 4, the second to last pile contributes 4 plus 4 is equal to 8, then 9 plus 8 is equal to 17, and so on, until we get the full array as 26, 24, 17, 8, 4. This gives us the cumulative stones available from each index. Next, we initialize a memoization table, DP, to store intermediate results and avoid redundant calculations. The recursion begins with Alice at index 0 and m equals 1, which means she can take either 1 or 2 piles. If she takes 1 pile, the function recursively considers Bob's turn with the remaining stones and m updated. Similarly, if she takes 2 piles, the recursion explores the new state. This branching continues as we explore all options for maximizing Alice's score. In the second branch where Alice takes 2 piles, we call DFS 2, 2 to explore Bob's turn. Here, m is updated to max 1, 2 equals 2, allowing Bob to take up to 4 piles. The recursion proceeds by exploring all possible moves for Bob, and this process continues until we reach a base case, either the end of the array or when all stones are taken. As the recursion unwinds, the intermediate results are stored in the DP table, ensuring that if a state like DFS 1, 1 is encountered again, we can fetch the pre-computed result directly from DP, saving computational time. This dynamic programming approach ensures that we avoid redundant calculations while systematically evaluating the best moves for Alice. By the end of the recursion, we determine that the maximum stones Alice can collect in this example is 10. Now, let's consider another example with piles equals 1, 2, 3, 4, 5, 100. Here, the suffix sum is calculated as 115, 114, 112, 109, 105, 100, representing the total stones remaining from each index onward. A memoization table DP is initialized to store intermediate results. The recursion begins with Alice at index 0 and m equals 1, giving her the choice to take either 1 or 2 piles. If she takes 1 pile, the state transitions to DFS 1, 1 for Bob's turn. Bob, starting with m equals 1, can also take either 1 or 2 piles, and the recursion explores these options. If Alice instead takes 2 piles initially, the state transitions to DFS 2, 2 for Bob, or his m is updated to 2, allowing him up to 4 piles. By systematically exploring these branches and storing results in DP, we efficiently calculate the maximum stones Alice can collect. For this example, Alice ends up with 104 stones by maximizing her score while minimizing Bob's opportunities. In a larger example with piles equals 10, 20, 30, 40, 50, 60, 70, 80, the suffix sum is computed as 360, 350, 330, 300, 260, 210, 150, 80, which gives the cumulative stones remaining from each index. A memoization table DP is initialized, and the recursion starts with Alice at index 0 and m equals 1. Alice can take either 1 or 2 piles, transitioning to states like DFS 1, 1 or DFS 2, 2. In DFS 1, 1, it's Bob's turn with m equals 1, so he can take up to 2 piles, and the recursion explores these options. In DFS 2, 2, Bob's m is updated to 2, allowing him to take up to 4 piles. As the recursion progresses, intermediate results are stored in DP, ensuring efficiency by avoiding redundant calculations. By the end of this process, we determine that Alice can collect a maximum of 210 stones, using optimal strategies at each step to maximize her gain while limiting Bob's options. This problem highlights several key insights. First, the suffix _sum array is crucial for efficient calculation of the total stones remaining from any index, reducing the need for repetitive summations. Second, memoization through the DP table significantly optimizes the solution by avoiding redundant calculations, which is especially important given the recursive branching structure. Third, the recursive strategy ensures that Alice can make decisions that not only maximize her immediate gain but also minimize Bob's potential score. This balance of maximizing Alice's score while limiting Bob's opportunities is central to the strategy. Finally, the use of memoization reduces the time complexity, making the solution feasible even for larger inputs, where exploring all possible moves without optimization would be computationally expensive. To determine the time complexity of our solution, we start by analyzing the recursive function DFS, index, m. This function relies on two parameters, index, which represents the current pile, and m, which is the maximum number of piles Alice can choose at that stage. The index variable can take values from 0 to n1, where n is the total number of piles. Meanwhile, the value of m can grow up to n because the constraint 2*m cannot exceed the total number of piles. This gives us a total of n*n, or n squared, unique states for the pair, index, m. Now, within each state, we have a for loop that iterates up to 2*m times. In the worst case, m itself can be as large as n, making the loop run n times. As such, the time spent per state is n in the worst case. When we combine the number of states and the time spent per state, we arrive at the overall time complexity of the solution. With n squared states in each state requiring up to n operations, the total computational cost is n squared n, which simplifies to n cubed. This is the final time complexity of the solution. Next, we turn to the space complexity. First, we consider the suffix _sum array. This array is used to efficiently compute the remaining stones and requires n space, where n is the number of piles. Then, we have the memoization table, or DP, which stores results for each unique state, index, m. Since there are n squared unique states, the space required for this table is also n squared. Another component of the space complexity is the recursive call stack. The maximum depth of recursion is determined by the progression of the index variable, which can range from 0 to n1. This means the recursion stack consumes up to n space. When we combine these factors, the overall space complexity is the sum of the space for the suffix sum array, the memoization table, and the recursion stack. This adds up to n for the suffix sum, n squared for memoization, and n for recursion, resulting in a total space complexity of n squared. To understand the efficiency of this approach, let's compare it to a naive solution. A brute force approach would involve exploring all possible ways to distribute the piles, which leads to an exponential time complexity of 2 to the power of n. This is because at each step, Alice could choose between 1 and 2*m piles, creating a branching factor proportional to the number of piles. In contrast, our optimized solution leverages memoization to store results of previously computed states, eliminating redundant calculations. By combining this with efficient computations using the suffix sum array, we reduce the exponential complexity to a manageable polynomial time complexity of n cubed. Finally, let's analyze the best, average, and worst-case scenarios for this solution. In the best case, the game concludes quickly, such as when the number of piles, n, is small. This reduces the number of recursive calls and states to process, though the asymptotic complexity remains n cubed. For both the average and worst-case scenarios, the solution must compute all possible states, index, m, and evaluate up to 2*m choices for each state. This results in the same overall complexity of n cubed. The mathematical reasoning behind this lies in the fact that the DFS function explores all combinations of index and m, leading to n squared states. Each state involves up to n operations, giving us a total time complexity of n cubed. Memoization ensures that each state is only processed once, preventing exponential growth. Similarly, the space complexity is dominated by the dp table, which stores O n squared states, resulting in a space complexity of O n squared. When tackling this problem, there are several common mistakes that you should be aware of. First, many assume that the problem can be solved with a simple greedy approach, where taking the maximum stones available on each turn guarantees the best result. However, this overlooks the long-term impact of the opponent's moves and can lead to suboptimal outcomes. Next, it's critical to understand the dynamic nature of the variable m. Remember, m doubles after every turn, which directly impacts the number of piles a player can choose from. Misinterpreting this can lead to invalid strategies. Additionally, solving this problem recursively without memoizing intermediate results can cause the time complexity to explode to O2 to the power of n, making it highly inefficient for larger inputs. Memoization is key to reducing this to O n squared. Another pitfall involves confusing the alternating turns between Alice and Bob. Each player has a unique perspective, and failing to alternate correctly can result in logical errors. Finally, incorrect implementation of base cases in recursion, such as when only one pile is left, can lead to runtime errors or incorrect results. Being vigilant about these mistakes will greatly improve your solution's accuracy and efficiency. Now, let's dive into some insights that can help you approach this problem effectively. At its core, this is a minimax problem, where the goal is not just to maximize your own score, but also to minimize the score your opponent can achieve in future turns. Balancing this trade-off is critical, as each decision impacts not only the current game state but also future possibilities. The problem also has an optimal substructure, meaning it can be broken down into smaller sub-problems. At each step, you need to decide how to maximize your stones while anticipating and accounting for the best possible moves your opponent might make. Dynamic programming is a powerful tool here. You can use a dp table where dp, I, m, represents the maximum stones a player can collect starting at index I with the current value of m. Recognizing patterns in two-player game problems can also give you an edge, as many of these problems involve similar recursive decision-making and memoization principles. If you want to explore related problems, consider LeetCode 877, which is a simpler version where players pick stones from the ends of the array, or LeetCode 486, which also uses dynamic programming in a two-player scenario. For more advanced variations, LeetCode 1406 and 1563 extend these concepts with additional constraints or strategies. Finally, let's discuss some alternative approaches and their trade-offs. One approach is to use recursion with memoization. This method is relatively easier to implement, as it follows the natural recursive structure of the problem, but it may be less efficient than iterative DP for very large inputs. Both methods have a time complexity of O n squared, but iterative DP avoids the risk of recursion stack overflow, making it a more robust choice for larger datasets, even though it might require more effort to code. It's also worth noting that greedy heuristics, while fast, are not a viable solution here. They often ignore the opponent's future moves, resulting in suboptimal outcomes. In terms of complexity, both recursive memoization and iterative DP have a time complexity of O n squared and a space complexity of O n squared, primarily due to the DP table. Understanding these trade-offs will help you choose the best approach based on the constraints and requirements of the problem at hand. Great job! To wrap up, we've tackled problem number 1140, Stone Game 2, and explored how dynamic programming can help optimize decision-making in competitive scenarios. Remember to practice similar problems to deepen your understanding. Thanks for tuning in, and don't forget to like, share, and subscribe for more content. See you next time. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!